Hi guys, this is Math 148 and we're still working on section 10.4, which is maximizing and minimizing in these various situations. And this is a question I wanted to go over that we're looking at maximizing volume. So this is very similar to example number 3 in your book on page 677 of the 10th edition textbook. And this is question number 21, and it says the base of a box needs to be twice as long as it is wide. The volume of the box is 256 cubic inches. The material for the top costs 10 cents per square inch. The material for the sides and bottoms costs 5 cents. Find the dimensions that will minimize the cost. Again, I have so many questions. If someone brought me this problem and said, mathematician, you must minimize the cost, I would say, what are you shipping? Why does it have to be twice as long as it is wide? Don't you want to look at other shipping and distribution, outlets if you're trying to minimize your costs? So if you had some of those questions, again, I think that's a really practical thing to do, to think of the bigger picture instead of just mathematically cranking through if you're in a real life situation. But for this, it isn't really so much real life, is it? It's just a math problem, but it's a playful one. We get to draw a picture of a box. So here we are. Question number, Question number 21. I'm going to draw a box for you. Here's the situation. Here's our box. Okay, this is, just so you know, I'm not very good at drawing things in perspective. But here's a little box. And I was trying to have it be twice as wide as it is, or twice as long as it is wide. How did they phrase that? Twice as long as it is wide. Okay. So twice as long as it is wide, and then we're going to just have some little height here. So here's our box. And we also know that the material, let's see if I can fill it. The material, that didn't work at all. The material here, I'll just do it this way. That's one side, is going to be, let's call that the top. The top of the box is 10 cents. And I noticed when your book did this problem, they just used 10 and called it 10 cents, and it simplifies things. So don't write 0.10. So it's like $10.10, write 10 cents, it makes it easier. And then the material for all the other sides, all this stuff, is 5 cents. So all that is 5 cents. So again, similar to what we did with the fencing problem, we're going to write two different equations, and then in order to maximize the volume, we have to write our volume equation in terms of one unknown. So here's what we have so far. We know our volume, this is a little geometry which you probably haven't done in a while, is going to be each side. So it's this side times this side times this side. So it's x times 2x times the height. You're saying, I don't know what the height is. The height there. Again, think of the height if you turn the box up on its top there. So that's going to be 2x squared times h is the volume. All right? And this tells us, we also know that if you flip this around, this tells us that h, the height, is 256 divided by 2x squared, because we know the volume is supposed to enclose 256 cubic inches. Again, I'm going to show you where that is in the problem. See right here, the volume is 256 cubic inches. Ta-da! So we have the volume is this function, 2x squared times h equals 256. That means the height is 256 divided by 2x squared. Why did I do that? Why would I do that at all? Well, because we are trying to minimize the cost here. I think we're trying to minimize the cost. Yep, find the dimensions that will minimize the cost. So we're not trying to maximize the volume, we're trying to minimize the cost. So minimize cost, that is our ultimate goal. So what is the cost of this box? Well, the cost, and assume that it's all equal dimensions, it's not thicker on top, the cost of the box in terms of x is going to be equal to all the sides together. So you have a top side, and the cost of the top is going to be 10 cents times the area of the top, which is 2x times x, right? I added this side, it's the top, plus these big sides here. You have this big side, that one right there, That's going to be 5 cents times, what are the dimensions of that side? 2x times h, and there's two of these. There's one on the front and then there's one on the bottom there. So we'll times 2. You'll notice I have 6 sides to my box. 1, 2, 3, 4, 5, 6. So here we have the top. Here we have sort of the wide sides. There's 2 of those. So I've added 3 sides. So I'm going to add more sides. Now this skinny little side is kind of confusing to see. Again, there's h there. That skinny side is 5 cents to make it, and the dimensions of that skinny side are x times h, and there's 2 of those. There's one here, and then there's one on the other side there. So there's 2 of those, plus the bottom, which is going to be on that side, is the same dimensions as the top, but the price is different. So it's 5 times x times 2x, and there's only one of those. There's only one of those. So again, here, that's the bottom of the box. This is the top of the box, and this is the wide side. There's 2 of those, and this is the skinny side right there. And there's 2 of those. So when you work all this through and you simplify it, here's what you get. You get your cost function is equal to 30 x squared plus 30x times h. And you remember that h is equal to 256 divided by x squared. So this whole thing now equals 30 times x squared plus 30x times h, which is 256, divided by 2x squared. I should have just gone ahead and written that as 128. That's 128 over x squared. It sure is. Okay, hold on. I need a new piece of paper. Here's our cost function for our box. We have the cost of x, where x is this side, is equal to 30 times x squared plus 3,840 divided by x. And again, the dimensions of our box are x, 2x, and then some height, where h is equal to 128 divided by x. So in order to find the minimum cost, we want to minimize our cost. We take the first derivative of the cost function. This is going to be equal to 60 times x minus 348, because you want to think of this x here. It's like x to the negative x, come on, to the negative 1. So it's minus 3,840 times x to the negative 2. So with a little bit of fancy math, you can rewrite this. So imagine multiplying both of these things, this one here by x squared over x squared. There. You get 660 times x cubed minus 3,840, all divided by x squared. Okay, that's the first derivative. And I simplified that. I kind of cut the step out where I simplify it there, but there it is. So the question is, when does this equal 0? What x value makes this equal to 0? Well, that's when you have 60 x cubed. This part's never going to be 0. And you can't have a dimension where the side is 0 anyway. So we're going to ignore the x equals 0 part and just look at, when does 60x cubed equal 3,840? Well, that is, so you divide everything by 60, right? Like that, 60. And then you take the cube root. You raise that all to the 1/3, and then you get x equal to 4. And we're ignoring the negative 4 component because it can't be negative. So x equals 4. You're very excited about this. That's a nice straightforward number. It always feels good. But we want to check now to make sure that this is a minimum. So our check to make sure that that's a minimum, you can do the sign test. Here is 4, and we have the first derivative. Let's pick a point on this side. I'll take 3. The first derivative evaluated at 3, so I'm plugging 3 into there, right? That's going to be negative 246. That's negative. I wrote all this out on my notes here so you guys can look at the notes online. So that's negative. So it's going down. The first derivative evaluated at 5. I'm picking 5 just because it's an easy number that's on the other side of 4. That gives me 146.4. The value doesn't matter so much as the sign, which is positive. So we know that our function goes down, then it hits 4 and it goes up. So we have confirmed that 4 is a minimum. A value of x equals 4 minimizes the cost. So are we done yet? Not quite, because if you look at the problem, it says find the dimensions that will minimize the cost. So if you just write 4, that's not the right answer, because 4 by itself is not the dimensions of a box. So hold on, I'm going to draw one more picture. Here again. So we decided that x equals 4 minimizes the cost. And so we had 4 is on this side was 2x, so we know this side is 8, and we had the height was equal to 128 divided by x, which now is 128 divided by 4. If you plug in x equals 4 in there, you get 8. So the dimensions of our box are 4 inches by 8 inches by 8 inches. And if you drew a picture like this, that would be awesome, or you can write your answer like this. Either one of these things are fine. So good job finding the dimensions of a box, and there's one more problem about inventory control that I will do next.